Welcome to the review for Chapter 4, Electron Arrangement. The test will consist of multiple choice, electron configuration, and then, of course, the problems of the two equations we have in class. The electron configuration, you'll have to do both within the multiple choice and on the short answer problems. And then the two equations, you'll be given those equations along with the constants, but you do have to know how to use them, and you have to know what the parameters are defined as. So before we get started, I need to give a shout out to Matthew Sellers in first period. He's going to actually do the review this time, so let's everybody say good job to Matthew Sellers when we see him in the hallway. Okay, so here are the definitions you need for the test. Remember, you can find the definitions in the chapter summary in your textbook. So go look up your textbook and go to chapter 4, chapter summary, hit go, and then you'll see these different definitions that you need. One thing that I want to remind you of is make sure that you know that wavelength is that funny looking upside down Y that we called lambda, and that frequency we designated as V. You will get the equations that use those on the test, but you need to know what the parameters are defined as, and you'll need to know how to use them. All right, so this equation, find the wavelength of light with this frequency of 3.20 times 10 to the 15th second minus 1. I want to remind you that a second minus 1 is the same thing as a hertz, okay? And so we are going to use this equation. We are going to rearrange to solve for wavelength. So we want to solve for this. So we will take wavelength, and we will say that it is equal to C over V. Whenever you are rearranging the speed of light equation, the speed of light, C, will never ever be on the bottom. It's always going to be on the top. And of course, it is defined as 3.00 times 10 to the 8th meters per second. And I want to remind you that the speed of light is a constant, meaning it is the same for all forms of electromagnetic radiation, where we're talking about microwaves, gamma rays, visible light, all the same speed for all of those. And so you can use that for any of them. And then we're going to put in frequency on the bottom. And we are going to say it's times 10 to the 15. Second minus 1. So then those seconds cancel out. And when I do that math and I use the correct number of significant figures, I should get that my answer is 9.38 times 10 to the negative 8 meters. And since it asks for it in meters, we're going to leave it in meters and not convert it. This one also needs to use that speed of light equation, although this time we're solving for, frequency. And so what I would like you to do is pause the video if you haven't already worked this problem and work it out and see if you get the correct answer. I want to remind you that because this wavelength is in centimeters right here, it needs to be converted to meters. Because the speed of light is meters per second, you must also have your wavelength in meters. So go ahead and pause and work the problem and see if you get it correct. All right, how'd you do? So when you converted the wavelength, you should have gotten that it was to a negative 8, and then you plug that in. Remember, I told you speed of light will never go on the bottom, always be on the top. So we take our speed of light and we divide it by our wavelength. Our meters cancel out, and then we are left with 4.00 times 10 to the 15th second to the minus 1, or hertz. We usually say hertz, but I need you to recall that that is the same thing. All right, this one says what is the energy of a photon with this frequency? So we're going to use the E is equal to hv, and of course that's Planck's constant, where h is equal to 6.626 times 10 to the negative 34 joules times second. You will be given this equation, and you will be given the constant, but you have to know how to use them properly. And so this is literally, we're just going to multiply these two numbers. So we plug in the constant times the frequency that they gave us, and then we answered in the correct number of significant figures, which would be 2.9 times 10 to the negative 17 joules. Okay, so this particular question, you actually have to know a lot about this. This is going to come, actually a couple of questions from the test will come over this information. The first thing is that the line emission of any atom is produced when the electrons are moving from the higher energy state, which is the excited state, and they are falling back down to the ground state. And so when they do that, they emit these photons at specific wavelengths that are specific to that element, and they're specific to how much energy was absorbed and then released. The second thing is that because hydrogen always produced the same spectrum, scientists concluded that hydrogen only produces photons with certain energies. And of course, they went on to apply that to all the other elements. That was what we did in the flame test lab. In the flame test lab, remember, certain metals, when they were excited by the heat and energy from the Bunsen burners, they would burn in a specific color. And of course, the one that was the highest energy level was the potassium, because it was purple. And then the red would have been the lowest energy level. And so that was able to conclude that there were energy levels and that there were electrons existing in these specific energy levels. And then the last thing that you need to know concerning this question is that Bohr developed this model, his model, the Bohr models that we drew in class. He developed that to actually explain hydrogen's line emission spectrum. The problem with Bohr's model is it actually only worked for hydrogen itself, but that was what he was trying to do, was explain the line emission spectrum for hydrogen. All right, so this says when an electron blank energy, it goes from the ground state to the excited state. And of course, we've been talking about this. So whenever it absorbs energy, it will go from the ground state to the excited state. So it absorbs energy and it jumps up to a higher level. Then when it falls back down to the ground state, it releases energy in the form of a photon. So it falls back down. And of course, we see that as light. All right, so how many electrons can one orbital hold? And the answer to that, which we've talked about many times in class, is 2. Okay, it holds 2 electrons. Remember, we would draw an orbital, and then we would say we would draw one arrow up and one arrow down. And so it would hold 2 electrons. It doesn't matter when we're talking about one orbital in the S, one orbital in the P, one orbital in the D. Always one orbital will hold 2 electrons, one spinning up and one spinning down. Okay, so first of all, let me apologize about the blurriness of this particular slide. When I scanned in the review, for some reason it's very blurry. So let's just get on with this. For each sublevel, it wants to know how many orbitals and how many electrons are within each sublevel. And so for the S, there is 1 orbital and it holds 2 electrons. In the P, there are 3 orbitals and it will hold 6 electrons. In the D, it is 5 orbitals and it holds 10 electrons. And in the F, it's 7 and it will hold 14. And when we say number of orbitals, that's what we would draw, like we would draw an S as one line, we drew a P as 1, 2, 3, and then we did a D as 1, 2, 3, 4, 5. So each one of those orbitals can hold 2 electrons, and so that's how we get that there's 3 orbitals holding 6 electrons, because we could have 1, 2, 3, 4, 5, 6. So 6 total electrons in there. And so make sure you know that for the test. That will come in handy. What is the maximum allowed electrons in each of the energy levels? And remember, we did the chart in class and we talked about that. When we want to know number of electrons in an energy level, we do 2n squared. And so for energy level 1, the maximum amount of electrons it could hold would be 2. For energy level 2, we do 2 squared, which is 4. And 4 times 2 would be 8. For energy level 3, we would do 3 squared, and then we would multiply that by 2, and that would be 9 times 2 is 18, so that value would be 18. And then the last one, 4 squared is 16 times 2 is 32. So energy level 4 could hold a maximum of 32 electrons. So the main difference between a 3D and a 4D sublevel is that the 4D is at a higher energy level than the 3D. That means they both still hold 10 electrons. A 3D will hold 10, a 4D will hold 10 electrons. But the 4D is at a higher energy level than the 3D, and that is the main difference. So I want you to please spend some extra time memorizing these 3 rules, because every year these rules catch kids on the test and they get them wrong. And it's not that they don't know the rules of electron configuration, because clearly they do, because they do really well on the electron configuration, but they don't know which rule is which. And so please spend the extra time. The first one is the Aufbau principle, and the Aufbau principle states that you fill the lowest energy level first. So that's why we always start 1s and then 2s and then etc. And then that's also why we would fill a 4s before we fill a 3D, because it's a lower amount of energy. One way that might be able to help you remember this is its Aufbau principle. And so we could think of, we bow to the first level, which is 1s, because that's where we start everything. I know it's kind of silly, but it might work. We bow down to the lowest energy level, so that's Aufbau. The second rule is the Pauli exclusion principle, and it is the rules that state that 2 electrons must have opposite spin when they are in the same orbital. So that's why we draw the arrows up and down, because they have opposite spin. And so a way you might be able to remember that is, once I put 1 electron in that orbital, now that is excluded from ever having another up orbital. Okay, it's very exclusive. They can only have 1 up and 1 down, and that's all that's allowed. And then the last one is Hund's rule, and Hund's rule is the one that states that everybody gets 1 electron before they can get another one when you're in the same orbital. So let's say I was filling a 2p over here, and I had 4 electrons to put in there. I would say 1 up, 1 up, 1 up, and then I would give a second one down. And so everybody has to get 1 before they can get another one. The word Hund is a German word for dog. I don't know if that'll help you remember anything, but maybe you figure everybody's got to have 1 dog before they can have a second dog. I don't know. It's just every year these 3 questions trip people up. So please spend the extra time studying these definitions. Okay, so using our chart, we are going to do the electron configuration. I'm going to do the first one with you together, and then we'll pause the video and I want you to do the next ones. But remember, you do not get to have this chart for the test, so you do have to have it memorized. But by now, most of you probably already have it pretty close to being memorized. So we start always with the first level, which is 1s2, so we're going to calcium. And so we're going to go 1s2, which calcium is right. Where is calcium? Oh, goodness. Calcium's right here. This is going to be calcium. So we're going to say 1s2, 2s2, 2p6. Then we go to 3s2, 3p6, and then we end in 4s2. So now pause the video and you do the other ones. So there is the rest of those configurations, their electron configurations. Now let's do their noble gas configurations. So whenever we are doing the noble gas, we always go and use the noble gas that comes before the element that we're looking at. So if calcium is right here, we would be using the noble gas that comes right here, which is going to be argon. And so we would say argon in brackets, okay? And then we would say 4s2. All right, so let's do the next one. This time we're going to do oxygen, which oxygen is right here. We would use the noble gas that comes before it, which is helium, and helium is a noble gas. So we would do helium, and then we would do 2s2, 2p4, and then I want you to pause the video and do the next two yourself. All right, so hopefully you got neon 3s2, 3p5, and neon 3s2, 3p6. On the test, when you are asked to do your electron configuration, and you will be asked to do both the electron configuration and the noble gas configuration, please read very carefully. If it says write the electron configuration, then you are going to do it this way. That is where we do the whole thing. If it tells you to do the noble gas, or sometimes it might say shorthand, that means a shortcut, then that means you do this particular way when you use the noble gas in brackets. When you are trying to find the noble gas configuration of a noble gas, notice you still use the one that came before it. So this was argon right here, this was neon. That is the noble gas that comes before it. So just make sure you read that very carefully on a test. All right, so these questions were kind of worded a little funny. You just had to think about them. Number 13 says, which element contains a full second energy level? So the full second energy level would actually be a 2s2 and a 2p6. And if we go look and see what ends in 2p6, we would find that it's neon. Question 14 says, which element contains a third d electron? So what that means is, actually it could have been a couple of things. A third d electron, we're going to say it's 3d3 because that's the first one we get to, but that question should have been more specific and tell us what energy level. So we're just going to assume that it's the first energy level that a d shows up in, and that would be vanadium. Which element would have 5 electrons in the fourth energy level? And so that would be the first 5 electrons that would go in the fourth energy level. So we would say 4s2 and then 4p2 because it says in the fourth energy level. So that would be germanium. 16 says, which element has 3 unpaired electrons in its first energy level? Okay, so that would have to be a p3 because in order to even get to p3, we have the s orbitals already paired. So we would say 1, 2, 3 up. And so if we go look at 4p3, we would see arsenic. 17 says which element has 7 electrons in its 5d orbitals. So that'd be 5d7, and that's iridium. And then the last one says which element has its outermost electron in 6s1. So that just means it ends in 6s1, which would be cesium. So here's just a couple other things that I want to make sure we stress. The first one is that make sure that you understand that wavelength and frequency are inverse, meaning if one goes up, the other one goes down. So sometimes you got to really talk yourself through that one and ask you a question like if something has a longer wavelength, what kind of frequency it has. And so make sure you're able to talk yourself through that they are opposite relationships. Also recognize when you're doing the calculations, please recognize that a hertz is the same thing as a second minus 1. We write it like this because it's easier to show how the seconds will cancel in our calculations. And then the last thing that I want to make sure you know today is that when you have 8 electrons in the outermost s and p orbital, we call that an octet. It means they have 8 in their outer ones. When you do have 8 electrons in your outer octet, they end up being noble gases. Okay, and here's 2 examples. Neon's configuration is 1s2, 2s2, 2p6. The outermost s and p orbitals, which means it has the highest number in front, is going to be 2s2 and 2p6, which add up to 8 total electrons, which is how many valence electrons the noble gases have. Again, if you had argon, you'd have 1s2, 2s2, 2p6, 3s2, 3p6. So that outermost orbital, which is the 3 level, and it's a 3s and a 3-2, gives you 8 electrons. So it's an octet, and those would be noble gases. That is why they are so stable and they don't react, because they have an octet and they makes them very, very stable. Okay, stay tuned for the jokes on the next slide. All right, time for the jokes, and shout out to 5th period for noticing that last time I forgot the joke. So these go out for especially for 5th period. All right, here we go. How do trees get on the internet? Well, they log on, of course. What did the horse say when he tripped? Help! I've fallen and I can't giddy up. And then the last one, what did Tennessee? The same as Arkansas. All right, good luck on your test. Make sure you study. I will see you in class.